Probability. Probability is a very important topic in statistics. In fact, when we talk about statistics, you have to understand that statistics exist a lot because of uncertainty. Okay, they exist because of uncertainty. And if things were constant in life, if everything was constant in life, then there would be no need for us to apply probability concept or even apply statistical knowledge. Because things are uncertain, because there are variation in life, this is why we need probability. Now, what are we going to do today? We are going to make a brief introduction to probability in the first part of this video. And then we will also discuss in the second part the another theorem that we call the Bayes theorem and the total probability theorem. So let's start by introducing the concept of probability first of all. I guess that many of you already have an idea that when we talk about probability, we are measuring uncertainty, right? We are measuring uncertainty. Now, when I say we are measuring uncertainty, what does it mean? It means like all measures that exist, we have a scale. If you take, if you want to measure your table, you would have a scale that you can use to measure that table. But in the same vein, when we talk about probability, there is a measure that you can use to, when we talk about uncertainty rather, there is a measure that we can use and it is probability. Now, when we talk about this measure, the measure will always lie between 0 and 1. Okay? What does it mean that the measure will lie between 0 and 1? It means that probability cannot go below 0, cannot be a negative value, it cannot go above 1. If you are calculating a probability for a certain event to occur and you get, let's suppose, 0, that would mean that this event is sure not to occur. All right, you have a certainty that it is not going to occur. All right, it's absolutely impossible. But if it is 1, then it means that you are sure that this event is going to occur with absolute certainty. If you get a value of 0.5 for a certain event, then it means that the event is equally likely to occur. In fact, to introduce some of the theory in probability, it is very important that we understand a few notations, all right? A few notations and also a few notations related to set theory. Now, to be able to understand some of these notations related to set theory, we will start by defining a few things first, all right? A few things that have to be defined. The first thing is an experiment. Now, when we talk about an experiment, what do I mean by an experiment? If I say I want to select a group of 3 students from the class. Now, the selection of the student can be considered as an experiment. But when we refer to probability, normally we are referring to the computation of probability based on an experiment which is random. I did not mention it there. I did not mention that here, but just for information, the not the event, but the experiment rather should be random. It's very important that you understand that there is a difference between randomness and haphazardness, all right? These are two different things. If I were to select student randomly in your class, maybe I'll just give you one way of doing it. There are other ways as well. I could take all your name and put it in a basket, and then when I've put all your name in a basket, then I will shuffle that, I will just mix these names properly, and then I will just select 2 people or 3 people, whatever I needed out of it. But here, when I did that, you understand that it is random. What does it mean by it is random? It means that every individual in the basket here has the same probability of being selected. However, when we talk haphazardness, there is bias. right? There is a bias here when we talk about haphazardness. If I select people at haphazardly, I may have a bias when I'm selecting people haphazardly. It might look like it is random, but it may not be random. Okay, there could be haphazardness. It could be there is a bias there in when we refer to um, haphazardly selecting people. So each time when we are referring to probability, we are not talking about any kind of experiment, but we are talking about an experiment that is random. Another example to refer to a random experiment is if you have a pack of cards and you want to evaluate the probability of drawing a queen from the pack of cards. You have to understand that if this has to be evaluated, this probability has to be evaluated, the experiment should be random means that the selection of a card should be based on a random process, which means that the card in themselves should be well shuffled. This is when the card will be random. All right, this is where the experiment will be random rather. So the experiment will be random only when the cards have been well shuffled. If the cards have not been well shuffled, then the idea of computing probability would not make much sense in this context. So remember, when we refer to an experiment, we are referring to experiments that are random. All right. The next thing is about an outcome. What does an outcome mean? All experiments that you carry out will have an outcome. Like if you toss a coin, you will have either a head that will occur or a tail that will occur. And if you are interested in the head, for example, then an outcome that you're interested in is the head. All right. But if you're interested in the tail, the outcome that you're interested in is the tail. But in any case, you have two outcomes, two possible outcomes here. Now, when we see that we have two possible outcomes, the thing is when you are tossing the coin, you have no idea what outcome will occur, right? You have no idea what outcome will occur. So because you have no idea what outcome will occur, it means this is where you need rather the computation of probability because there is uncertainty attached to this outcome, to the result of your experiment, okay? And the other thing that you need to understand, which is very important, is the sample space. Now, when we refer to the sample space, also known to as a probability space, at times we write it as S, at times we write it as omega, all right? At times we write it as omega, at times we write it as S. In any case, if you see something like S or omega in the context of probability, you know that we are referring to a sample space or a probability space. Now the question is, what is a sample space and what is a probability or what is a probability space? The same thing, huh? What is it? It is an exhaustive list of all possible outcomes. This is what the sample space mean, an exhaustive list. Exhaustive means all the possible outcomes have been taken into account. If I take, for example, this case, if I toss a die and I say these are the outcomes that I have, all right, if I say that these are the outcomes that I have 2, 4, 5, and 6, you would understand that this is not the sample space. This is not the sample space. We cannot say that this is the sample space. Why? Because there are missing outcomes. When we talk about the sample space, we are referring to all the possible outcomes. All the possible outcomes means you have a 1, 2, 3, 4, 5, and 6, then it becomes a sample space. All right. If you have some outcomes missing, then it is not a sample space. All right. So what is a sample space? A sample space is a list of all the possible outcomes. This is what I mean by exhaustive. And the other thing is, if you talk about a subset of this sample space, then you will understand that this is referred to as an event. An event is generally defined by a capital letter. For example, the case of a die itself. If you take the case of a die, if you have a sample space equal to 1, 2, 3, 4, 5, and 6, all right, then if you say let's define A as the even number, okay, even number, then what is going to happen? If you define A as the even number, then the thing is A is going to be equal to 2, 4, and 6. Now, if you look at A and you look at omega, which is your sample space, you will see that A is a subset of omega. This is why we define A as an event. Any subset of the sample space is what we refer to as an event. Now, these are very important concepts. Why it is important? Because this is where people make mistake when they are doing when they are taking exam questions on probability. They either wrongly define their outcome space or their event space rather, or they wrongly define the sample space. This is why you have to be careful when you are reading a question. You should not misinterpret your sample space, and you should not misinterpret your event space as well. Normally, I ask you the question if if you have understood the how do we call, if you have understood the sample space. Now, before I ask you this question, let's understand something. When you are showing a sample space, you will have to use a curly bracket to give a list of all the outcomes. This is where you come to the concepts of sets theory, all right, where you have a list of possible outcome, and when you are going to write down the list of all the possible outcome, each outcome will be separated by a comma, obviously, all right. Each outcome is separated by a comma. So when I'm going to ask you the next question, and when you're going to answer me when you're going to give me your solution to the answer to the question, please do me the favor of always having a curly bracket in your solution, and also each outcome separated by a comma. Each outcome should be separated by a comma. So what is the question that I want to ask you to see if you really understood what a sample space is? It's very important that you understand what a sample space is, because as I said to you, it is based on the sample space and the event space that you are going to compute probability. If you got one element less in your sample space, you will wrongly calculate probability. If you got one element less in your event space, you will wrongly calculate your probability. So this is why I say it's very important. Now, how would I know if you understood that? This is why I ask you to do a question on Google Classroom about sample space, right? I asked you the question, consider the random experiment of tossing a coin 3 times. Then you are asked to define the sample space of this experiment. This is going to be available on Google Classroom. So you can do that for me. It is labeled activity 1. I repeat, it is labeled activity 1 in Google Classroom under the probability section. Okay, under the probability section, it is referred to as activity 1. You will be marked normally automatically on that. You will understand if ever you are getting it wrong, but we can discuss it in the tutorial time if needed. Okay, this is one way to see if you understand what a sample space is. Now, when you are writing down head, you don't need to write down HEAD, please, or you just need to write H. If you are referring to tail, just write T. If you are referring to head, just write head as H, all right, but not T. Not head, not tail, but T and H. And then I also ask you to state the outcomes of the events of obtaining at most 2 head. Now, to be able to know that, you will basically this will depend on that. Now, this is not a question on Google Classroom, this one, but we will take it in the class, okay, just to see if you got it right. We will take it in the class. Now, as I said to you earlier, we have to understand a little bit about sets theory to be able to compute probability. Why? Because if you refer to, for example, the concept of union, the concept of intersection, the concept of the complement of an event, all right, all these different concepts are concepts that we are going to use when we are going to compute probability. For example, I might be interested in the probability of either an event occurring, let's suppose A, or another event occurring, let's suppose B. Now, just hear what I said. The probability, which I will use P here to refer to probability, that an event A has occurred or an event B has occurred. Now, when I say O, you will see that I don't need to write down probability of A or B, or I don't need to write down things like that, probability of A or B. I don't write these kinds of things. I don't need to write even this kind of thing. I can just use the sets theory to be able to describe whatever I want to do. All right, so we have a mathematical notation here that we are using, which is based on sets theory. This is why you need to understand what this union is. You need to understand what intersection is and complement of an event is. So basically, when you say either A or B, you have to understand that both could also occur. Let's suppose we refer to the example of selection of, again, a random process where you have to select a lecturer from the Faculty of Social Sciences and Humanities. And let's describe this as A, all right? Is a lecturer from Faculty of Social Studies, Social Sciences and Humanities. And let's describe B as a male lecturer. These are two different events. One is a lecturer from Faculty of Social Sciences and Humanities, and B is a male lecturer. So when I say A union B, what do I mean? I mean either the lecturer is from Faculty of Social Sciences and Humanities or is a male lecturer. But you have to understand when I say or, that does not exclude, I repeat, that does not exclude the fact that there might be lecturers who are male from FSH, right? From the Faculty of Social Sciences and Humanities. So, in other words, it means that when we refer to O, it's inclusive. The A and the B, like A and B together, if we want to use this word together, is a possibility. Like there is this possibility of having a male lecturer from Faculty of Social Sciences and Humanities. So when we talk about either or, we are not excluding this possibility of having both, right? Sometimes what people do is that they forget when they are evaluating the probability of A union B, they forget this possibility that both could occur. And this is where it's wrong. So be careful. When we talk about A or B, it does not mean A separately and B separately. No, it means either A or B, but also both. Intersection B is used to describe the probability that both A and B occurs. Like in the case that we are referring to here, A intersection B is equal to male lecturer from FSSH, all right? This is what it means. A intersection B means male lecturer from FSSH. If you look at it from a Venn diagram, you would understand what I'm referring to. And then A dash means, by the way, when we talk about A dash, we could also write it like a superscript C, and we could write A bar. All these refer to the complement of an event. What does it mean by the complement of an event? If I say A is A represent lecturer from Faculty of Social Sciences and Humanities. So what will happen to um, what will happen to a bar? A bar is what? A bar means, or a bar or a dash. A dash would mean what? A dash would mean all lecturers from all faculties excluding those from FSSH. A bar or a dash means lecturers from all faculties except Faculty of Social Sciences and Humanities. If I say B dash means, if I say B dash means female lecturer, that is not male. If I say A dash, it means not lecturer from FSSH. In other words, all lecturers from all faculties except FSSH. And if I say B dash, it means all lecturer who are not male. That's basically what dash means. And then you have also this symbol, this Greek symbol phi, which is supposed to represent the null set. All right, the null set means there is nothing in there. It's empty. It's an empty set. And why do I say all this? Because the probability of an empty set is equal to 0. Okay, so that's a little bit about sets notation. So what's the next step now? The next step is to discuss a little bit about the A intersection B that we just saw. The A intersection B that we just saw, we will come up to a term that we call mutually exclusive events. Now, two events are said to be mutually exclusive if the occurrence of one precludes the occurrence of the other. All right, precludes the occurrence of the other means it prevents the other from occurring. It prevents the other from occurring. Like if you refer to the case of M is a male lecturer and F is a female lecturer, you would understand that M intersection F is the null set because you cannot have a lecturer. If you have selected a male lecturer, by default, it has prevented you from selecting a female lecturer because if you are selecting one person, only one person. The moment that you have got a male lecturer, it's over. You don't have a male and a female at the same time. This is what I mean by preclude. It prevents the other from occurring. So it's equal to the null set. But if you look at the previous example that I took here, if you say A represent male lecturer and B represent, A represent lecturer from Faculty of Social Sciences and Humanities and B represent male lecturer, you would understand that A and B is not the null set. It's not the null set because it exists that one does not, it exists that you have a male lecturer from FSSH. It means that A does not preclude the other from occurring, or B doesn't preclude A from occurring. It doesn't prevent one from occurring. If you have selected a male lecturer, that does not mean that you cannot get a lecturer from Faculty of Social Sciences, Humanities. So in this context, A and B, A and B is not equal to the null set. It's not equal to the null set. So they are not mutually exclusive. They are not mutually exclusive here. But in the context of male and female, you would understand that these two events are supposed to be mutually exclusive. So if they are mutually exclusive, then when you take the probability of M intersection F, you will see that you are supposed to get 0 because the probability of a null set is always equal to 0. All right, the probability of something that cannot occur is equal to 0 because we already mentioned it a little bit in the first instance when we define probability of 0 and 1. So this is just intuitive in any case. That's what we refer to as mutually exclusive events. These are important terms because you will get to understand that when we come to axioms of probability, we will need this concept of mutually exclusive events. So as I said to you, mutually exclusive event means that the two sets that we have, A and B, are disjoint sets. All right, they are disjoint. The next question is how to measure probability. Measuring probability is relatively simple. If I take the case of, you have another example that is given here that you can read, but let me take the example of a die. If you take the example of a die, 1, 2, 3, 4, and 5, and 6, sorry, and you take the case of an event which represents an even number, and I call it E. You have 2, 4, and 6, all right? So if I want to find the probability of getting an even number, look at the way I write this down. I put a P to represent probability. I put a bracket to enclose the event, right? Because P is representing the probability measure. P is representing the probability measure of the event E. And what is the event E? According to this definition, it is saying that we need to look at the cardinality of A by the cardinality of S. What is cardinality of A and what is cardinality of S. All right. What do I mean by cardinality of A and what do I mean by cardinality of S? Now, for this particular example, I did not use S as the notation. I use sigma. So I will use sigma, not sigma, excuse me, omega. So I will use omega down there as well. So the cardinality means the number of elements in that set A. What is the number of elements in that set E? Not A, but E, excuse me. What is the number of elements in the set E? The number of elements in the set E is 1, 2, and 3. So you will have 3 in the numerator divided by the number of elements, that is the cardinality of omega. What is the cardinality of omega? You have 6 elements there. So it is 3 out of 6. Obviously, it is half. Just to let you know, this is why I mentioned earlier that you should be able to define your sample space properly and you should be able to define your event space properly. If you wrongly define those, you will see that you will not get the correct probability. Let's suppose I forgot that there was 6 in there. Let's suppose I forgot that there was 6. So what would have been the answer? 3 out of 5, which is completely wrong. So this is why you have to be very careful in your definition of your sample space. This is how to measure probability. I give you a set of activities, obviously, and this first activity, for the random experiment of tossing a coin 3 times, what is the probability of obtaining more than one head? I will leave it to you to do it on your own. Why? Because normally this activity, you got part of it to be that you need to do on Google Classroom. So if I give you the solution right now, you will be influenced in your answer to on Google Classroom. Okay, so I'll leave it for later. Please just remind me all these activities that I did not discuss so that we can discuss it in the class in the tutorial. Okay, so the probability that a senior citizen, let's take this one. The probability that a senior citizen in a nursing home without a pneumonia vaccination will get pneumonia is 0.45. Now, we can call this event senior citizen in a nursing home without a pneumonia vaccination. We can define this as A, right? And we are saying that the probability of A equal to 0.5. So not having a pneumonia is defined as A, let's suppose. What is the probability that a senior citizen without pneumonia vaccination, right? Earlier I said uh, without a pneumonia vaccination, okay, will get pneumonia. But now I'm saying, what is the probability that a senior citizen without pneumonia vaccination will not get pneumonia? Will not get pneumonia. Now, if he gets pneumonia is A. And if it doesn't get pneumonia, it's obviously we are referring to as A dash, and it becomes 1 minus 0.5, which is equal to 0.55. So that is the solution that we have for the probability of a person without a pneumonia vaccination that will not get pneumonia. Now, there is not much computational probability here, but it is just to, we did not really apply this concept that we just saw here for the time being. Okay, we're going to apply that in a moment. But this was just to illustrate what we learned here, all right, in terms of the complement of an event. If I say an event A has a probability of 0.4, then the event not A has a probability of 0.6. Why? Because all probability sum to 1. If all probability sum to 1, this is why I can subtract this. If A was 0.45, then A dash becomes 1 minus 0.45. Now let's apply this concept that we just learned here in an example. What is the probability of drawing an ace from a well-shuffled deck of 52 playing cards? Now, let's look at this well. Well-shuffled, all right? Well-shuffled means what? It means that the experiment is random. You are asked what is the probability of drawing an ace from a well-shuffled deck of 52 cards. Now, the question that you need to ask yourself is, this is what we said, how many ace do we have? If we define A as ace, how many ace do we have, and we need to also know what is the number of elements in our sample space. So here, the number of elements in our sample space is very clear. It is 52. So we have 52 in the denominator. And what is the number of ace that we've got in a pack of cards? So a pack of cards is divided into different shoots. One of it, for those who don't know, is a club, and the other one is a spade. And then you also have the heart, and you also have a diamond. These are the different shoots of a pack of cards for those who don't know it. Eh? You can go and check it online if you want to have a better idea of how it look like. So you have a club, spade, and heart. Now, when we refer to club, spade, and heart, they are distinguished by different numbers. For example, you would have um, you would have ace is one possibility, 2, 3, up to 10, and then you have a king, the jack, and the queen, or king, queen, jack, king, queen, jack, rather. Okay, these are the different possibilities that we have. We have 8, 2, 3, up to 10, and then king, queen, and jack. So you will see here that there are 13 cards in all for the club. You have to understand that this repeat itself for the spade, and repeat for heart, and repeat for diamond. Each of these different numbers are going to repeat. Now, we have a shoot. These two shoot here are black shoots, black cards. All right. If you look at it on the internet, you will see that they are black, and these two are red cards. So this is just for your information, if in case you have to compute questions on related to cards, to a card setting. Now the question is, what is the probability of drawing an ace? You need to ask yourself, how many ace do I have? I have one for club, but I also have one for spade. I also have one for heart, and I also have one for diamond. So in other words, don't forget that this whole thing here repeat itself for spade, for heart, and for diamond. So how many? What is the probability of drawing um, an ace from a well shuffled deck of 52? So the sample space is 52. The number of ace that we have is 4 out of 52, which can simplify obviously. And then I also asked you, if A, let A be the event of drawing a queen from a well-shuffled standard deck of playing cards, and B the event of drawing an ace card. Are A and B mutually exclusive? This I leave it to you to determine. How would you know if two events are mutually exclusive? Let me just remind you, we need to be able to show that the two events, the probability of the intersection of the two events equal to 0. That's how we determine that. So you need to evaluate whether, when you're looking at the probability of A intersection B, do you get 0 or do you not get 0? Maybe I will just give you a solution because it's relatively simple to understand. So I'll just explain it to you and give you the solution immediately, okay? When I say are A and B mutually exclusive, how would I know if they are mutually exclusive? If the probability of A and B is not equal to 0, they are not mutually exclusive. If they are equal to 0, they are mutually exclusive. So let's define A as the event queen and B as the event of drawing an ace. Now, if we refer to the queen, we already see here there is one queen from club, another queen from spade, another queen from heart, and one from diamond. We also have the same thing, a ace for club, a ace for spade, and an ace for diamond. The question that you need to ask yourself, if I draw a card, if I have obtained a queen, can I at the same time be getting an ace? When you look at it, you would understand that this is not possible, because if you have selected a queen, if you've drawn a queen, obviously it precludes A from occurring. A cannot occur, but you can have a queen of a club, right? So if we refer to club as an event and queen as another event, we can obtain a queen from a club, which means that they are not mutually exclusive. But in our context here, you cannot have an ace and a queen together. That doesn't make sense. So the probability of A and B equal to 0 in this context. So they are mutually exclusive. So let's talk about axioms of probability now. Axioms of probability. What is an axiom? When you hear this word, it's something that you are seeing for the first time, this word axioms. Now, this word axiom is a Greek, comes from a Greek word rather, okay, that we refer to as axioma. It comes from a Greek word that we call axioma. And what does it mean? It means that it is meant to be trivial. That's basically what it is meant, what it means. It is meant to be trivial, which means it is thought worthy or fit or that which commends itself as evident. All right, it is thought worthy or fit or that which commends itself as evident. It is considered to be something that is trivial. We don't have to argue on it as if. All right, this is what we refer to as axioma. It's something trivial. It's like that. It has to be like this. And in fact, there are three axioms of probability, which basically is going to help you in understanding why, for example, probability lies between 0 and 1. Why probability lies between 0 and 1. Now, we will understand that, especially from the first two axioms, right? When we refer to these axioms, they are also referred to as the Kolmogorov axioms, all right? Kolmogorov axioms. Now, it's just a name, don't worry. In fact, you will see that these seems new to you, but they are not very complicated. They are very basic and simple things to understand. They are supposed to be trivial. They are supposed to be easy to understand in any case. Now, when we talk about probability, the first axiom states that the probability of an event is non-negative. The probability of an event is non-negative means that the probability of A is greater than or equal to 0. It is very important that you understand that I used the word non-negative. Many people would say that probability is positive. If I ask you if probability is positive, right now, many of you will tell me yes, probability is positive. But this is not totally correct. You should not say that probability is positive. It's not the right way of saying things. You should say that probability is non-negative. The question that we would ask ourselves, what's the difference between non-negative and what's the difference between positive? Let me explain. Probability that an event is non-negative is what you see here. But if you tell me that probability is positive, understand this well. If in case you tell me that probability is positive, you are saying that probability of an event is greater than 0. That's what you mean. If you tell me that probability is positive, this is what you are saying. Look at the difference between this and this. When you say probability is positive, you are telling me that 0 is not included because 0 is not a positive number. So if you say that it is positive, you are not allowing 0 in your definition. But when you say it is non-negative, it changes the whole thing. When you say it is non-negative, it allows 0 to be included in the definition because even 0 is not negative nor positive. So it allows this possibility of having 0 in the definition. So this is why you have to be careful. Whenever you write down things, if I ask you an exam, write down the axioms of probability. Do not tell me that probability is positive. This is wrong. You should tell me that probability is non-negative, or you can just write this down. The second axiom is the probability of a sample space equal to 1. This is quite logical and simple to understand. If you take any element from your sample space, like the case of tossing a die, if you take either one occurring or the other occurring and so on, the probability that you will get either one occurring or the other occurring and so on should be automatically equal to 1. So this is what we refer to as the sure event. And this is what we refer to as the event is sure not to occur. But this one is sure that the event, not sorry, excuse me, the probability of 0 is the event is sure to occur, but not this one. I did something wrong. Careful. But I was saying that the probability of omega equal to 1 is what we are referring to as the sure event. You cannot have something that goes above 1. If we take the sample space, remember by definition what the sample space means. It means all the possible outcomes. So you cannot have something above all the possible outcomes. You cannot evaluate probability based on something above all the possible outcomes. All means all. So in other words, it is supposed to be equal to 1. It's why now we say that this is based on these two axioms that we say that probability of an event A is between 1 between 0 and 1, because you see that you cannot have something that goes less than 0, but you cannot have something that goes above 1. So this is why we always learned that probability is between 0 and 1, because these two axioms makes this clear. And of course, not only does it makes it clear, it's also intuitive to understand. So but if I ask you the actions of probability, don't give me this. This is the result of these two actions. If I ask you the actions of probability, you have to write down as they are here, all right? Don't write down the consequence of the two actions. The next actions is about the concept of mutually exclusive event that I mentioned to you earlier. Now you will see some crazy kind of definition of terms here, but let me just simplify things for you. If you have a sequence of mutually exclusive events, let's suppose E1, when I say En, it means n can take any value, right? E1, E2, E3, E4, etc. All right? That is, when we say mutually exclusive event, means E1 intersection E2, where 1 is not equal to j, I is not equal to j, I is not equal to j. So in other words, I can't talk about E1 and E1. This is why I'm saying E1 and E2, or E1 and E3, or E1 and E4, or E2 and E5, or E2 and E1, whatever. But as long as I is not the same as j, is equal to the null set. This is what we refer to as mutually exclusive, as I explained to you. Like for in the previous case, A intersection B equal to 0 is equal to the null set, means that A and B are mutually exclusive. But here, the only difference is that I'm extending notation. I'm not writing only for two events, but I'm saying EI intersection EJ is equal to the null set. EI intersection EJ is like, let's suppose you have E1 intersection E2, right? Or E3 intersection E5, or whatever, as long as they are not equal. Now, if you take a series of mutually exclusive events, as we just said, now we are not referring to only two, but we are extending this notation for more. If you have two, it's simple, like what I wrote up here, what I wrote here. But if you have more than two events, you can use this notation as you are saying. Then, if these events are mutually exclusive, as we have defined it, the probability of the union of n is equal to 1 to infinity is equal to the sum of the probability of ENs to occur. So the probability of a union is equal to the sum of the marginal event. Maybe you might be a little bit afraid about what is written here. Let me just show you what it means. It's just like you use the concept of sigma is equal to 1 up to n of xi. This means what? x1 plus x2 plus up to xn. But in the same vein, when you refer to the probability of union of ENs, what does it mean? It means the probability. Another way of writing this down, instead of writing it in this compact form, you can write it down like this. You start by n is equal to 1, so En means E1, and then you have union. So you have union, what else? What's the next step? N is equal to 2, so you have union E2, you have union E3, and you go on like that. You have union E3, excuse me. you have union, it goes on like that to infinity, right? Infinity means you put dot 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 because you won't know where it ends. And then this is equal to what? So this is what I just wrote here. This means that, all right? Maybe you will be understanding this better, but just for information, this is a more compact way of writing all this here. And then this is equal to what? It's equal to, it's telling me that it is equal to the sum of the marginal probabilities. So what is the marginal probability? Again, you replace n is equal to 1. So you have the probability of E1. And then what do you have? Added with the next one plus, what's the next step? E n is equal to 2. So the probability of E2 plus probability of E3 plus it goes on like this. So that is what this is stating. It is stating that the probability of a series of mutually exclusive events, E1 up to E infinity, all right, would be equal to the probability, the sum of the marginal probabilities. Marginal means they are alone, like probability of E1, like probability of E2, they are marginal. That is what it means by the sum, by the third axiom. The third axiom is just stating that the probability of a set of mutually exclusive events is just equal to the sum of the marginal probabilities. All right. So if A and B are mutually exclusive, so what does it mean in concrete term? If A and B, let's suppose E1 is A and B is E2, all right? E1 is A and E2 is B. So the probability of E1 union E2, let's suppose you have only two possible letters of n takes only two possibilities. So the probability of E1 union E2, where E1 is A and E2 is B, just names, all right, is equal to what according to this definition? If A and B are mutually exclusive on here, if they are mutually exclusive, it means that the probability of A union B equal to the probability of A plus probability of B, and you are done. That is what the third axiom states. Quite simple to understand. Next step is, this is why, by the way, when I use this letter P, I'm using it under the assumption that we are dealing with a probability measure. A probability measure means it has to satisfy all these three actions. In other words, the probability cannot go beyond 1, cannot go below 0, for example. And you cannot have, for a set of mutually exclusive event, you cannot have anything else apart from this rule here, right? So then we will say that P, this is why I can allow myself to write P of A. I can write P of A because P is considered as a probability measure if it satisfies this axiom. That is, if in the end I did not get, for example, negative 0.1. If I get negative 0.1, P is not a probability measure, right? We cannot say that we are computing probability. We are not computing probability if it is equal to negative 0.1. So that's a little bit about the actions of probability. Actions, as I said, it is a little bit, there are theorems in statistics, but theorems are meant to be proved. But here, there is nothing like that. You don't have to prove these. You just use them, right? So these are what we refer to as actions of probability. Our next step is to refer a little bit to this from a different perspective. We'll get back to this action from a different perspective now, which is the general law of addition of any two events, right? When we refer to the general law of addition of any two events, I think this is relatively easy to understand. Why? Because let's talk about, first of all, a case where the events are not mutually exclusive. If you take a Venn diagram, let's suppose you have, no, let's make it simpler, only two events for the time being. Make it simpler. You have A and B. And if I say, what is the probability of getting either A or B? basically what I'm asking you is all this shaded part here. So this is what I refer to as the probability of A union B. Probability of A union B refers to, from sets theory, this shaded part, which means that you are taking the all A that you get here, which is the probability of A in terms of probability, plus you are taking this all B, which is probability of B in terms of probability. But you would have to understand, because you've taken A and you've taken B, this small part have been taken twice. So obviously, you cannot take it twice. You cannot double count something when you're computing the probability. This is why, because you're double counting it, you have to remove it once. All right. You take probability of A plus probability of B minus probability of A intersection B. So that is the general law of addition of any two events. The question is, when do you apply this? You apply this when the question has something to do with either or. If you have a question in probability which relates to either one event occurring or another event occurring, this is where you apply this rule. Because there are cases where you're not interested in either or, but you are interested in and A and D. Then it's a different story, right? When you are interested in A and D and instead of O, it's a different thing. But now we're talking about O, either O, which means that this is a rule that you need to apply. Now, but just imagine something. Let's suppose A and B, they are mutually exclusive events. So A and B is a null set. What would happen to this? You can already reply in your mind that this is equal to 0. You will understand that this is equal to 0. So if this is equal to 0, what do you get in the end? This is where you get probability of A plus probability of B if A and B are mutually exclusive. I repeat, if they are mutually exclusive. If they are not mutually exclusive, you still need to apply this. But if they are mutually exclusive, then you apply that directly. And if you look at this carefully, you will see this is what we just discussed here, which is the third axiom of probability. So this is related to the general law of addition of two mutually exclusive events, rather not two, but mutually exclusive events. I give you an example here, which is on self-study that you can read on your own, which is about the case of drawing an ace or a king. O, you will see the word O. This is what I want to draw your attention. You see, the word O means A-O, union. And the moment that you see that you have to apply probability of A union B, you already need to understand that you will have to apply the general law of addition of any two events, which is probability of A plus probability of B minus probability of A intersection B. That's the first thing that you need to remember and get into your mind. But the only thing that you have to understand is that in this specific example here, A and B is going to be equal to 0. So this is why you don't see it there, because in the end, A and B are mutually exclusive. So this is why it's getting direct to that. But in any general setting, do not forget this part, A intersection B. Do not forget that. This is where many people get it wrong, because they forget this A intersection part. But here, in any case, if you were to write it down, you will get 0, and it will be the same thing as 2 out of 13. So this you can read on your own, and I give you some activities here that you would have to do on your own, and we will discuss that in the tutorial, all right, session. So just remind me to discuss these activities when we meet. We are going to discuss all of them, each of these activities that I did not discuss. Just remind me when we meet. And then we have the conditional probability. Now, what is conditional probability? Okay. The concept of conditional probability is important in statistics when we refer to probability, because sometimes there are people who confuse a lot of these terms. People sometimes confuse union for intersection. People confuse conditional probability for intersection. There are so many confusion that arise sometimes in the concept of probability. So this is why you need to understand what a conditional probability is clearly. Let me just take an example to illustrate this concept of conditional probability. Let me just write it down. Let me just create a, a new sheet, and then I can write it down and explain it to you. Okay, here we go. I'm going to take an example to explain this concept of conditional probability. Okay, what example would I take? I will take an example. Let's suppose you are in a class. You are in the class of a few students, and students are excuse me. Students are you're in a class of students where you have male students and female students. Okay, or let's put it like this: students are wearing black shirt and students who are not wearing black shirt. You have male students and you have female students, or M dash. All right, write it as M dash. So I'll just take some numbers just like that, haphazardly. Here we go. We have something, let's suppose, like this, okay, where you have 50 individual in a class. You have in all you have 40 who are wearing black shirt and 20 who are not wearing black shirt. Okay, and then you have male student and you have female student. So you have 15 male student and you have 35 uh, female student. If I ask you what is the probability of, I'll just take a few examples before I come to the concept of conditional probability. Yeah? If I ask you what is the probability of a student wearing, what is the probability that a student is wearing black and is a male? The probability that a student is wearing black and is a male is what? You count how many B and M you have, which is 10 out of the sample space, which is 50, which is 1 out of 5. This is done. What is the probability that a student is not wearing black? So the probability that a student is not wearing black is basically equal to 20 out of 50, 2 out of 5. The probability that a student is either wearing black or is a male. You see there's a difference between this one and this one. The probability that a student is either wearing black or is a male. How do we determine that? We determine that by taking, there are two ways of going about this. One way is by applying the general law of addition that we learned, probability of A plus probability of B minus probability of A intersection B. So this in this case is probability of B plus probability of M minus probability of B intersection M. This is one way of doing things, all right? Probability of B uh, plus probability of M minus probability of B intersection M. You can go ahead with that, but it's the lengthiest process in this example because you could just easily do it visually. Probability of B union M, you can just do that later on and see if you get the same solution like I'm getting now. If I say probability of B union M, B union M is equal to what? Probability of B union M, you look at all the B's that you have. These are the B's that you have. And what are the M's that you have? How many male do you have? You have 15 males, you have 30 wearing black. But notice something, you see that this is been counted twice again here, there is a problem. So what you have to do, you have just to count the number of cardinality of B union M. The cardinality of B union M is what? The cardinality of B union M is this. The cardinality of B union M is 30 plus 5, which is 35 out of 50. You can just check it out by using this formula and you will see you will get the same solution, because visually I can do it. But you would understand that not always can I do things in a straightforward manner like I did here visually. At times, I need the formula to be able to do that. Okay, I need this formula at times. So this is the probability of B union M. This is the probability of B intersection M. This is the probability of B dash. This is the probability of B union M that I said. Okay, but let me just talk about something else now. Let me ask you another question now. What is the probability that a student is wearing black? What is the probability that a student is wearing black if he is male? What is the probability that a student is wearing black if he is a male? What does it mean? I'm still interested in the probability that a student is wearing black, but there is a difference between this. I'm not asking you what is the probability that a student is wearing black and is a male. Because if I ask you the probability that a student is wearing black and is a male, another way I could ask that is what is the probability that a male student is wearing black? This is the same thing. A male student is wearing black, or a student wearing black is a male, is the same thing. So there you see that it is 10 out of 50. Look at that, out of 50. But if I ask you what is the probability that a student is wearing black if he is a male, there is a difference. If means what? There is a condition now. There is a condition that you have set. The condition is that you are still calculating probability that a student is wearing black, but there is a condition. If he is a male, so you put that like this: given is a male. We use this notation here, this bar, to show that there is a condition. So when you put this bar here, there is a condition that you are showing. You are not evaluating probability of B from the 50 now, but you are evaluating the probability of B from this 15, which means that out of male now, what's the probability of B? Not out of the 50, not out of everything, but out of 15, what's the probability of B? So, in other words, out of a male, given male means out of 15. You have how many who are wearing black? It is 10 out of 15. So this is the difference. Look at this and look at that. They are two different things. It's all about how you read a question in probability that matters. You have to read the question well. If you read it wrong, obviously your answer would be wrong. So, because you would not understand what's asking you. So please ensure that you understand the difference between a conditional probability and an intersection, a union, a complement, or whatever. Okay, there are different things there. So that is what we refer to as the conditional probability here. Yes, when I say probability of B given M is equal to 10 out of 15, you could use this formula that you see here. This formula would also give you the same probability. What does it mean? The probability of A given B equal to the probability of A intersection B over the probability of B. Look at that. The condition goes down in the denominator always. So if I said what is the probability of B given M, and I want to use this formula that I just showed you, B given M, it would mean the probability of B intersection M over the probability of M. That is what it is supposed to be. Remember, the condition goes in the denominator. So let's try to see if we get 10 out of 15. What's the probability of a male? Probability of male is 15 out of 50. We are just trying to see if this formula give me the same solution that I got just visually, right? 15 out of 50. Now the probability of B and M, we already did it 10 out of 50. So in the end, you see that it is equal to 10 out of 15, just like we just saw visually. So this is another way of dealing with conditional probabilities by using this formula, because not always shall you have such a straightforward case like you would have a table and you can find the probability in a matter of seconds. No, things are not always going to be like that. So you will always need to have an alternative, which is, for example, this formula that helps you to do so. This is another question that I'm going to ask you to do afterward. You can do it on Google Classroom and you get the solution there, okay? So our next step is independent events. I'm just going to be very brief about it because it's on self-study. I'm going to be brief about it, okay? Independent events, basically, when we refer to an independent event, it means that the occurrence of one event of this event does not have any impact or does not have any effect on the occurrence or the probability rather of occurrence of the other event. All right, I give you some examples here. That's what you read. So the occurrence of one does not have an impact on the occurrence of the other. But basically, when two events are independent, this is one of the ways that you would be able to identify this. If two events are independent, you just need to check for the joint probability, that is the probability of A intersection B, and you look at the product of the marginal probabilities. Marginal means they are on their own. Probability of A alone, probability of B alone, the product. So if the product of these marginal probabilities is the same as the joint probability, joint means intersection, then you would say that these two events are independent. Now, you might ask yourself, but where does this rule come from? Maybe some of you already remember it at high school, but the thing is, where does this rule come from? How did we get such rule to say that the two events are independent? I'm going to discuss that later on when we come to the multiplication rule. Then you will understand what it is. But before I get to that multiplication rule to be able to explain that, it's important that you understand this. This means what? The probability of A given B, if A and B are independent. By definition, what is independent? Independent means the occurrence of B has no impact on the occurrence of A, or vice versa. All right? Occurrence of B has no current impact on occurrence of on the probability of occurrence of A. So if A and B are independent, if I say probability of A given B and B and A are independent, it's the same thing as probability of A. Why? Because whether you put the given B or you did not put the given B, this would have no impact at all on the evaluation of the probability of A because it's going to be the same thing. All right. So this is why intuitively, if B has no impact on A, there was even no need for us to say to write this down, this part here. There would be even no need for this because if they have no impact on each other, basically probability of A given B is just equal to the probability of A, or vice versa. Vice versa that you see here. So that's intuitive. B has no current impact on A, which means that the probability of B will have no impact on the probability of A. The occurrence of B rather will have no impact on the probability of occurrence or non-occurrence of A. There is no change. Probability of A will still be probability of A, whether B exists or whether B doesn't exist or whether B appears on the scene or not. It will still be A. It won't change. So this is why you have an activity here to prove that two events are independent. We'll get to that in tutorial. Please try it out first. And remember what I just said here. You need to evaluate this part here. You need to evaluate this and show that they are equal. If they are equal, they are independent. If they are not equal, they are not independent. So this is how you carry on with this activity. There is also a set of activities here. Answer this on Google Classroom again, please. You will get all these questions on Google Classroom. So the solution will be available. But the only thing that I might be discussing with you is this part, because I guess this one you will have some trouble with it. So I will discuss that in the tutorial session. Just again, remind me about it. Remind me for this one as well. Now we get to the multiplication rule. That's what I was going to explain to you, right? The multiplication rule. we have seen earlier the addition rule, right, which says that probability of A union B equal to the probability of A. This is what we saw. Now listen to me well. When you say or, we have been applying the addition rule. But now we are going to look at the case of AND. If A and B, what's the probability of A and B? Many of you have been stuck with one thing. Many of you, when you think about what is the probability of A and B, many of you will think about that. Many of you think about that. And you have to be careful. This is not the right way of doing things. If this exists only if these two events are independent. But if they are not independent, what you are writing here is wrong. So this is why you have to be very careful whenever you write down this case of intersection. When I'm asking for a question, what's the probability of A and B? You should not think about probability of A times probability of B directly. That is, you cannot think about this one. This one applies only, do not forget, for independent events. But here, this one is a general rule that I'm going to give you right now. I'm going to give you a general rule for the probability of A and B. But I'm not going to give you this one, right? I'm not going to give you this one right now. Probability of A times probability of B is for independent setting. If the events are not independent, you should not apply that. This doesn't make sense. This is only if the events are independent, or you can use it to check if the events are independent. But if the events are independent, that rule will make sense. But if the events are not independent, then you can't do that. So what do you do then? Let me just explain something to you. We learned something earlier. We learned that the probability of A given B is equal to the probability of A intersection B over the probability of B. We'll agree with that. Now, just for information, if we say probability of B given A, all right, it is equal to what? The probability of, again, A intersection B over the probability of A. I don't need to write this B intersection A because B intersection A and A intersection B are the same thing, by the way. But B given A and A given B are not the same thing because they are two different sample space. All right. B given A and A given B are not the same thing, but A intersection B and B intersection A are the same thing. So this is why I don't need to write down B intersection A. I can just write down A intersection B. Now, if we look at this one, let's have a look at this one for a moment. What is the probability of A intersection B? Probability of A intersection B equal to the probability of A given B times the probability of B. That is what we see. Now let's have a look at this one now. This one says the probability of A intersection B equal to the probability of B given A times the probability of A. So in other words, you have just seen something here. We are talking about probability of A intersection B. We are talking about the probability of A intersection B. But in the end, there are basically here two rules that gives me the same solution. A given B, A intersection B, and B is equal to B given A times probability of A is the same thing as probability of A given B times the probability of B. It's the same thing. There's no difference between these two things. All right. So this is what we call the multiplication rule. You see there is a multiplication here. So because there is a multiplication, we call that the multiplication rule. You're multiplying probabilities. This is a probability, this is another probability, you're multiplying them. Because you're multiplying them, we refer to them as multiplication rule. Now, just listen to me well. We said that you have to be careful. Do not write down, as I said, if you are given A and B, do not write down probability of A times probability of B. If you are given A and B, what you should think of is either probability of A given B times the probability of B, or you should think of probability of B given A times the probability of A, as I just explained. This is what you should think of. because this is a general rule whether the event is independent or not. Now, obviously, if the events are independent now, if the events are independent, what's going to happen? Let's take this first case. If the events are independent, we just learned something earlier. We said that the probability of A given B is equal to the probability of A. If the events are independent, then in other words, this becomes probability of A. This circle becomes the probability of A. All right? Now, if it is equal to the probability of A, we are done on one side, but then we need to multiply by the probability of B. Now, in the same way, if we are referring to the second equation, if the two events A and B are independent, this turns out to be probability of B times probability of A. It's the same thing here. So what's happening here? If the events are independent, this is the rule. Probability of A intersection B equal to probability of A times probability of B. This is what I explained to you earlier. How did you get this rule? This rule comes from the multiplication law. The multiplication law. This is the multiplication law that allows me to get this rule for independent events. So in other words, I can check whether two independent events are independent just by using this formula, all right, to check that. Now you understand where this comes from. Maybe some of you have always been using it at high school, but had no idea where this came from. You were just using it blindly. But now you know that it comes from the principle of multiplication rule, where intuitively A given B equal to A, or B given A is equal to B, probability of B. Then based on this, you get to replace that by probability of A or replace that by probability of B, and you get this solution. So this is a multiplication rule. You are asked to apply this activity. We are going to have a look at it, obviously, in the next when we meet on the tutorial. So this is the first part of the video. I'm going to send you another part of the video shortly, uh, but you can still work out these activities for our class. And if yes, you can work out these activities in the meantime for our tutorial session. So I'll next talk about the Bayes theorem in another video. Okay, thank you. Remember, please do not forget to do all these activities before we meet in the tutorial.